Hi, I'm Ajay and I'll be your pactor for Introduction to Real Numbers. Identification of various kinds of numbers is really important, and real numbers and its properties help us establish a known pattern so that favorable known outcomes can be established. These known outcomes become theorems. We'll be using the why effect, that is, what, why, when, where, who, and how, to complete our journey of real numbers and make you feel really comfortable with the basic theorems and concepts. Let's start with some facts. The assumption is that you have a good understanding about these facts. Natural numbers are the counting numbers like 1, 2, 3, and so on. Whole numbers are simply the numbers starting with 0, 1, 2, 3, and so on. 0 is not a natural number. Integers are like whole numbers, but they also include negative numbers. But still no fractions are allowed. A rational number is a number that can be expressed as the quotient or fraction in the form of p by q of two integers, a numerator p and a non-zero denominator q. Since q may be equal to 1, every integer is a rational number. Irrational numbers are numbers that cannot be expressed as a ratio of two integers. Fractions represent equal parts of a whole or a collection. For example, 1/2, 8/5, 3/4 are all examples of fraction. Numbers we can multiply together to get another number. They form the factors. A number can have many factors. For example, 6 has 4 factors: 1, 2, 3, and 6. Prime numbers are numbers that have only two factors, 1 and they themselves. For example, the first 5 prime numbers are 2, 3, 5, 7, and 11. Remember, 1 is not a prime number. By contrast, numbers with more than two factors are called composite numbers. Number 1 has only one factor, and thus it is neither prime nor composite. Let's take an example of a composite number. Say 15 has 4 factors: 1, 3, 5, and 15. Two numbers are considered coprime if the only positive integer that is a divisor of both of them is 1. For example, 3 and 8, or say 4 and 9. The common divisor between both of them is only 1. Theorem is a rule or principle, especially in mathematics, that can be shown to be true. HCF, highest common factor of two natural numbers x and y, is the largest possible number which divides both x and y. Example, HCF of 24 and 36 is 12. Least common multiple, LCM, of two numbers is the smallest non-zero common number, which is the multiple of both the numbers. Example, LCM of 2, 3, and 5 is 30. Let's start our journey of real numbers. So, what are real numbers? Numbers which can represent actual physical quantities in a meaningful way are known as real numbers. These can be represented on a number line. Number line is a geometrical straight line with arbitrarily defined zero, which is called the origin. Real numbers include all rational and irrational numbers. So the question would be, how to identify real numbers? Numbers which can be used to measure of varying quantities such as size, time, distance, etc. are real numbers. So all natural numbers are real numbers. All integers are also real numbers. All rational numbers are also real numbers. All irrational numbers are also real numbers. In short, any number which can be used to represent any quantity or number in real world is a real number. This course is about understanding the two properties of positive integers and using Lemma to establish other application to these properties. The two properties are Euclid's division algorithm and the fundamental theorem of arithmetic. But before we venture into Euclid's division algorithm and fundamental theorem of arithmetic, a very basic question that comes to mind is, what is a lemma? Lemma is a proven statement used to prove another statement or theorem. So it's like you want to prove something and you already know something. So you are using what you already know to prove the next statement. So going back to the property that we are trying to learn, what is Euclid's division lemma? So let's say a and b are two positive integers. There exists unique integers q and r such that a is equal to b multiplied by q plus r, where r is greater than or equal to 0 and always less than b. If a is completely divisible by b, then r is equal to 0. This can be restated as follows. Dividend, which is a, is equal to divisor, which is b, into quotient, which is q, plus r, which is the remainder. So a is equal to b multiplied by q plus r. It is important to note that in division lemma, q or r may be 0, but r is always less than b. So theorem EDL, this is just a WahPACT shorthand to remember Euclid's division lemma. So theorem EDL, Euclid's division lemma, is given positive integer a and b, there exists unique integers q and r satisfying a is equal to b multiplied by q plus r, where r is greater than or equal to 0 and always less than b. So if you remember, the property that we are trying to learn is Euclid's division algorithm, which is based on this lemma. So what we are trying to establish here is Euclid's division algorithm is based on Euclid's division lemma. But a very basic question that arises is, what is algorithm? A series of well-defined steps which gives a procedure for solving a type of problem is called an algorithm. It's kind of you have a pattern recognition perspective for solving a problem, and that series of well-defined steps form the algorithm for that. Now that we know what is algorithm, let's look at what is Euclid's division algorithm. Euclid's division algorithm is a technique to compute the highest common factor of two given positive integers. Euclid's division algorithm actually involves Euclid's division lemma and is applicable for only positive integers. To obtain the HCF of two positive integers, say c and d, with c is greater than d, we have to follow the following steps. So step 1 is apply Euclid's division lemma to c and d. So we find whole numbers q and r such that c is equal to d into q plus r, where r is always greater than or equal to 0 and is always less than d. Step 2 is to check if r is equal to 0, then d is the HCF of c and d. If r is not equal to 0, then we apply the division lemma to d and r again. Remember, it is d and r and not d and c. Step 3 is to continue the process till the remainder is 0. The divisor at this stage will be the required HCF. Let's take an example to really summarize what we have understood in these steps. So let's say we have a challenge where we have to calculate the HCF of 867 and 255. So as we know 867 is greater than 255, we apply the division lemma to get 867 is equal to 255 into 3 plus 102. So here q becomes 3 and the remainder r is equal to 102. Now the step 2 is to check whether r is equal to 0 or not, and obviously 102 is not equal to 0. So now we apply the division lemma to d and r, which is 255 and 102. To get 255 is equal to 102 into 2 plus 51. Now we again consider the new divisor as 102 and the new remainder as 51 and apply the division lemma to get 102 is equal to 51 into 2 plus 0. Now we see that the remainder has become 0, so our procedure stops. Since the divisor at this stage is 51, the HCF of 867 and 255 is 51. It is important to note that 51 is the HCF of 102, 51. It is also the HCF of 255 and 102, and it is also the HCF for 867 and 255. Euclid's division lemma has many applications. Let's take another example. Use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Let's look at the solution. Let x be a positive integer. Remember, that's an important assumption for applying Euclid's division lemma. Dividing x by 3, we can apply Euclid's division lemma and state that x is equal to 3q plus r, where r lies between 0 and can be equal to 0 also, but is always less than 3. Q is the quotient and r is the remainder on division by 3. Now the possible values of r can be 0, 1 or 2. Let's take the first scenario where r is equal to 0, which implies that x is equal to 3q. Squaring both sides, x square is equal to 9q square, which implies that x square is equal to 3 multiplied by 3q square, which in turn reminds us that x square is equal to 3 times of m, where we assume that m is equal to 3q square. Now let's talk about the second scenario where r is equal to 1. So if r is equal to 1, x is equal to 3q plus 1. Squaring both sides, x square is equal to 9q square plus 3q plus 1, which implies that x square is equal to 3 times 3q square plus q plus 1. Here we can see that x square is equal to 3 into m plus 1, where we assume that m is equal to 3q square plus q. Finally, we look at the third scenario where r is equal to 2. So x becomes 3q plus 2. Squaring both the sides, x square is equal to 9q square plus 6q plus 4, which implies that x square is equal to 9q square plus 6q plus 3 plus 1, which implies that 3 multiplied by q square plus 2q plus 1 as a whole plus 1 as a remainder forms it as x square is equal to 3m plus 1, assuming m is equal to q square plus 2q plus 1. It is time we continue with further journey of real numbers. This time, let's start with the other property, fundamental theorem of arithmetic. So what is fundamental theorem of arithmetic? We call it the theorem FTA. Every composite number can be expressed, that is factorized, as a product of primes, and this factorization is unique except for the order in which the prime factors occur. For example, 210 is equal to 2 into 3 into 5 into 7. The order in which the primes occur as its factor is not taken into consideration, as 2 into 3 into 5 into 7 is equal to 210, and also 3 into 5 into 7 into 2 is also 210, and similarly 5 into 7 into 2 into 3 is also equal to 210. So the order here has no significance. It is important to understand and treat this as a pointer. So the general rule is a composite number x, we factorize it as x is equal to p1, p2, p3 till pn, where p1, p2, p3, pn are all primes written in ascending order. That is, p1 is less than equal to p2 is less than equal to p3 and so on till pn. The same primes can be combined to give the powers of prime. For example, 16,380 can be written as 2 into 2 into 3 into 3 into 5 into 7 into 13, which is equal to 2 square into 3 square into 5 into 7 into 13. So here we have made sure that the primes are written in ascending order, and if the prime occurs again, can be combined to give power of primes. The order becomes unique based on the assumption that the order of factors will be ascending. It is a very important point to remember. A direct application of fundamental theorem of arithmetic is prime factorization method. So, what is prime factorization method? Prime factorization method is a process of factoring a number in terms of prime numbers. That is, the factors will be prime numbers. Least common multiple and HCF, highest common factor, can be calculated by this method. Let's take an example. Find the LCM and HCF of 10 and 24 by prime factorization method. The solution is 10, which can be written as 2 into 5, and 24, which can be written as 2 into 2 into 2 into 3 by prime factorization method. So the HCF of 10, 24 is equal to 2, which is equal to the product of the smallest power of each common prime factor in the numbers. LCM of 10 and 24 is equal to 2 cube into 3 into 5, which is equal to the product of the greatest power of each prime factor involved in the numbers. Now, if we look at an observation for any two positive integers a and b, the HCF of a and b multiplied by the LCM of a and b is actually equal to a into b. But mind you, this is not applicable for three numbers, that is, HCF of a, b and c multiplied by LCM of a, b and c is not equal to a multiplied by b multiplied by c. Now let's jump to irrational numbers. So what are irrational numbers? Real numbers that cannot be written as a ratio of two integers are called irrational numbers. It can also be stated that real numbers that cannot be written in the form of p by q, where p and q are integers and q is not equal to 0. So examples of irrational numbers are, for example, root 2 or root 3. These are all irrational numbers. How to prove irrationality of numbers? In order to prove the irrationality of numbers, we use a theorem based on fundamental theorem of arithmetic. We call it a theorem px square, which implies px. This is just to remember. So let's say let p be a prime number. If p divides x square, then p divides x, where x is a positive integer. Let the prime factorization of x be as follows. X is equal to p1, p2, p3 till pn, where all p are prime numbers and are not unique preferably, where p1 and p2 till pn are primes, not necessarily distinct. So if we do squaring of both sides, we have x square is equal to p1, p2 till pn multiplied by p1, p2, pn again, which is equal to p1 square into p2 square into p3 square till pn square. Given p divides x square and applying fundamental theorem of arithmetic, p is one of the factors of x square. Using the uniqueness part of the fundamental theorem of arithmetic, we see that p1, p2, p3 and so on till pn are the only prime factors of x square. P is one of p1, p2, p3 and so on till pn, which implies that x is equal to p1, p2, p3 till pn and p divides x. So we have proved the theorem that a prime number that divides square of a number also divides that number. This new theorem will be used extensively to prove the irrationality of other numbers. So let's take an example. Prove that root 2 is an irrational number. In order to prove this, we'll be using the proof by contradiction. In mathematics and applying logic, proof by contradiction is a form of proof that is arrived by assuming the proposition and then showing the proposition to be false, thus contradicting with the initial assumption. So if your assumption is incorrect, what you thought about would be as an inference of that assumption is also incorrect. Let's see an example of the proof by contradiction by proving the irrationality of root 2. Applying proof of contradiction, let us assume that root 2 is not an irrational number or it is a rational number. So if it is a rational number, root 2 can be expressed in the form of p by q or a by b, where a and b are co-primes, that is, their HCF is 1. If that is the case and we square both the sides, we see that 2 is equal to a square by b square, which implies that a square is equal to 2b square, which implies that a square is a multiple of 2. Now here, if we apply the theorem px square implies px, that means if there is a prime number that is part of the square of a number, then that prime number is also a prime factor of the root of the number. Taking that into consideration, we see that a is a multiple of 2. So let's mark this as equation 1. Now let's assume a is equal to 2c for some integer c. Squaring both the sides, we have a square is equal to 4c squared, which in turn implies that 2b squared is equal to 4c squared. And in turn, this is equal to b squared is equal to 2c squared. Now if that is the case, then b square is a multiple of 2 also. From 1 and 2, a and b have at least 2 as a common factor, but this contradicts the fact that a and b are co-prime. Because remember, co-prime numbers just have 2 factors, 1 and they themselves. This means that we are contradicting that root 2 is a rational number, which implies that root 2 is an irrational number. Let's look at some observations related to the irrational numbers. Square roots of all prime numbers are irrational numbers. For example, root 3, root 5, root 7, etc. are all irrational numbers. Sum or difference of a rational number and an irrational number is always an irrational number. For example, 7 plus root 3, 6 minus root 5 or 5 minus root 7 are irrational number. Product and quotient of non-zero rational and irrational number is irrational. For example, 3 multiplied by root 7 is equal to 3 root 7, or 4 root 2, 3 divided by root 5 or root 3 divided by 2 are all irrational numbers. Let's take an example. Show that 6 minus root 5 is an irrational number. The solution is applying proof by contradiction. Again, let's assume that 6 minus root 5 is a rational number and that can be expressed in the form of a by b or p by q. Here, for convenience, we are taking a by b, where b is not equal to 0, which implies that 6 minus a by b is equal to root 5. As a and b are integers, 6 minus a by b is rational, which implies root 5 also should be rational. But we know square root of all prime numbers are irrational. The contradiction exists because of incorrect assumption that 6 minus root 5 is a rational number. Thus we proved that 6 minus root 5 is an irrational number. Let's take another example to show 3 root 7 is irrational. Also show root 63 is also irrational. Again, applying proof by contradiction, let's assume 3 root 7 is a rational number which can be expressed in the form of p by q. Here we are taking a by b. So where a and b are integers and b is not equal to 0. A by 3b is equal to root 7. As a and b are integers, so a by 3b is also rational. So root 7 also has to be rational. But we already know root 7 is irrational as square root of all prime numbers are irrational. The contradiction exists because of incorrect assumption that 3 root 7 is a rational. So 3 root 7 is actually an irrational number. Also root 63, which can be written as root 3 into 7 is equal to 3 root 7, which implies that this also is an irrational number. In this quadrant, we'll be revisiting rational numbers and their decimal expansions. Before we go into more detail about decimal expansions of rational numbers, let's look at what is decimal expansion. The decimal expansion of a number is its representation in base 10, that is in the decimal system. In simpler words, it means converting a fraction or a whole number into decimal representation. Decimal expansion is represented in two ways: finite decimal expansion or terminating decimal expansion, infinite decimal expansion or non-terminating decimal expansion. So, what is terminating decimal expansion? If after decimal we have finite numbers, non-repeating digits, then it is termed as terminating decimal expansion. So let's convert fraction 1 by 2 into decimal expansion, which implies that 0.5, and that is non-repeating. Thus, after decimal, we have finite number and the decimal expansion terminates. So what is non-terminating decimal expansion? If after decimal we have infinite numbers and repeating digits, then it is termed as non-terminating decimal expansion. For example, 1 by 3 in the decimal form is equal to 0.33333 and so on infinite number of times, which is equal to 0.3 bar. Yeah, bar is a dash above the digit 3, which indicates that the digit 3 appears infinite number of times, which is repeating itself, and that is called non-terminating decimal expansion. Decimal expansion of rational numbers follows a pattern. If we are able to realize this pattern, then we will be able to help us look at a fraction and decide if it is terminating or non-terminating repeating. So what is decimal expansion pattern for rational numbers? Let's see the case of rational numbers. As we know, rational numbers can be expressed in the form of p by q, where q is not equal to 0. So decimal expansion is 2 to the base of 10. Prime factors of 10 are 2 and 5. All multiples of 10 can be written in the form of 2 raised to the power of n into 5 raised to the power of m, where n and m are non-negative numbers. For the form p by q, if q is divisible by 2, 5 or multiples of both, then the decimal expansion is terminating. So now we are formulating the theorem for decimal expansion of rational numbers. So the theorem is, let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form of p by q, where p and q are co-prime, and the prime factorization of q is of the form 2 raised to the power of n into 5 raised to the power of m, where m and n are non-negative integers. For example, 0.8, which is equal to 8 by 10, can be written as 8 divided by 2 raised to the power of 1 into 5 raised to the power of 1, which is equal to 4 divided by 5. We can see that 4 and 5 are co-primes. Another example can be 0.625, which can be written as 625 divided by 1000, which is equal to 5 raised to the power of 4 divided by 2 raised to the power of 3 into 5 raised to the power of 3, which finally is equal to 5 by 8. And again, we see that 5 and 8 are co-prime. It's about time that we start thinking in an inverse direction. This is a very important pointer. Once we start thinking from an inverse perspective, the same theorem can be rephrased as, let x equal to p by q be a rational number such that the prime factorization of q is of the form 2 raised to the power of n into 5 raised to the power of m, where m and n are non-negative integers. Then x has a decimal expansion that terminates. The example can be 4 by 5, which can be written as 4 divided by 5 raised to the power of 1, which is equal to 4 into 2 divided by 2 into 5, which is equal to 8 by 10, which finally is equal to 0.8. So we can see that if 4 by 5 is a rational number where q is of the form 2 raised to the power of n into 5 raised to the power of m, then the decimal expansion of the same terminates. But what if the prime factorization of q is not of the form 2 raised to the power of n into 5 raised to the power of m? n and m are non-zero integers, as I have already suggested. So now the theorem becomes, let x is equal to p by q be a rational number such that the prime factorization of q is not of the form 2 raised to the power of n into 5 raised to the power of m, where n and m are non-negative integers. Then x has the decimal expansion, which is non-terminating, repeating. In essence, it is recurring. For example, 1 divided by 7 is equal to 0.142857142857142857 and so on. Here we see there are repetitions of the digit 142857. In this case of rational number, if decimal is not terminating, then it must be recurring. But what about the decimal expansion of irrational numbers? Irrational numbers are the one in which decimal expansion is non-terminating and non-recurring. So finally we have real numbers can be rational numbers or irrational numbers. The rational numbers of the form p by q, where prime factorization of q is of the form 2 raised to the power of n into 5 raised to the power of m, where n and m are non-negative integers, the decimal expansion is terminating. If the rational number is of the form p by q, where prime factorization of q is not of the form 2 raised to the power of n into 5 raised to the power of m, where n and m are non-negative integers, the decimal expansion is non-terminating but repeating. And for irrational numbers, the decimal expansion is non-terminating and non-repeating. This brings us to the conclusion of the course, Real Numbers, where we started with two properties and discussed various patterns that will be helpful in understanding rational as well as irrational numbers. I would like to leave you with a pointer for this course. It is important that you acquaint yourself with the terms used and given as facts of the chapter. Understanding and feeling the terms will help you establish your basics about real numbers and the patterns. This course also acts as a stimulus to develop logical ability based on previously known and established lemmas or theorems. Hope you liked our presentation.